Hi everyone, my name is Raymond and I'm a graduate chemistry student and I'll be graduating next year in spring 2018.
And I'm Joey Presley. I'm a biochem student from the year of 2019.
So today we're looking at a question in your workbook. In particular, it's chapter 6.1 and the question is skill builder number 31. And so here's the question itself. Cobalt-60 is a radioactive isotope used to treat cancers of the brain and other tissues. The gamma ray emitted by an atom of this isotope has a wavelength of 9.32 times 10 to the negative 13 meters. And then we have parts A, B, C, D, and E. So we'll walk you through it, but at this point, you should pause the video, try to work through the questions yourself, and then just come back and we'll help you out. So the first question, part A, is asking us what is the wavelength in nanometers? And so what they give us, And so what they give us is 9.32 times 10 to the negative 13 meters. And basically what they want us to do is convert it to nanometers. And so both of them are units of length, so we just need to use a conversion factor, which is 10 to the 9th nanometers is equal to 1 meter. So as long as we set up the conversion correctly, we should be fine. So here's our wavelength, and we have 9.32 times 10 to the negative 13 meters. So we want to have meters on the bottom to cancel that out. So 10 to the 9th nanometers over 1 meter. So multiplying this through, the meters will cancel out, and our answer will be 9.32 times 10 to the negative 4th nanometers. And that's part A. So now that we have part A done, which gave us the wavelength in nanometers, we actually want to find the frequency in part B. And so the equation that we want to use is C is equal to the wavelength times the frequency. And C is the speed of light, so we can just rearrange this for the frequency, which is C over lambda. And just looking at units themselves, C is the speed of light, which is meters per second. And the wavelength is going to be a unit of length. So we'll end up with 1 over second as our final unit for the frequency. And actually, it's asking us for hertz, and a hertz is actually 1 over second. So the units check out. So anyway, let's substitute in the equation and see what happens. We have the frequency is equal to the speed of light, 3 times 10 to the 8th meters per second, divided by the wavelength, which we actually solved in nanometers. But since we have meters up here, we can just use the meters, and it'll cancel it out. It'll be a lot cleaner. So 9.32 times 10 to the negative 13 meters. Meters will cancel out, and then our answer will be 3.22 times 10 to the 20th, 1 over seconds. And I mentioned up here that a hertz is 1 over second. So this is the same as 3.22 times 10 to the 20th hertz. That's going to be our answer for part B.
Part C asks us about the energy of one photon in joules. So to accomplish this, we can use the equation energy is equal to hc over lambda, where h is Planck's constant, 6.63 times 10 to the negative 34 joules times seconds, and c is the speed of light, which is 3 times 10 to the 8th meters per second. And on the bottom, we have our wavelength. Now the problem asks us for energy in joules, so we want everything to cancel out except for joules. And in order to do that, we need to cancel out meters on the top with meters on the bottom. So we want our wavelength in terms of meters, which is given to us in the problem. So we're going to use 9.32 times 10 to the negative 13 meters. And so now seconds cancel out on top, and meters cancel out here, so we're just left with joules. And if we plug this in, we get a value of 2.13 times 10 to the negative 13 joules. Part D asks us for the energy of 1 mole of photons. Well, in part C, we just solved for the energy of a single photon, so we just need to multiply by Avogadro's number to get the amount of energy in 1 mole. So starting with our answer from part C, 2.13 times 10 to the negative 13 joules. Now this is per photon, so I'm just going to put per photon on the bottom. We can multiply by Avogadro's number, 6.02 times 10 to the 23rd photons per mole. So now our photons cancel, and we're just left with an energy in joules per mole, and that's equal to 1.28 times 10 to the 11th joules per mole. Part E asks us about the energy of 1 photon in electron volts. So what is an electron volt? An electron volt is just another unit of energy. It happens to be the amount of energy that one electron gains by accelerating through a potential difference of 1 volt. But we don't really need to know this to solve the problem. All we need to know is that 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So it's a rather small amount of energy. To do this, we can use the answer that we got for part C, which again was 2.13 times 10 to the negative 13 joules, and we can multiply by the conversion factor to cancel out joules. So we want joules on the bottom of 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. Now joules cancel and we get our answer in electron volts, which is 1.33 times 10 to the 6 electron volts.
And that's it.
Thanks for watching.
Yep.